Okay, in this presentation we're going to look at a binomial distribution question. Now, we're just going to read the question and sort of determine what sort of information we get, and we might sort of see that it is not actually not clearly a binomial distribution question. So, a very crude model for the distribution of claim size x in a particular situation represents x as a discrete random variable. So this sort of throws us in the wrong direction, and that's the sort of the point of the question actually. So if you read that discrete random variable and you try and proceed accordingly. Now actually you could actually use that approach and actually get the correct answer. But the most straightforward approach is actually to look at this from the point of view of a binomial. Anyway, sorry, I'm digressing here. So which takes the values 5,000, 10,000 and 20,000 where probabilities 0.4, 0.5 and 0.1 respectively. Calculate the probability of 5 randomly selected claims, that of 5 randomly selected claims, 3 are of 5,000 each and the other 2 are of larger amounts. So we're going to use the binomial distribution for this question. Okay, so there is actually some other approaches that you can take, but they're very long-winded. This is the easiest one. It's just actually knowing that it is binomial. So here what we're defining as success is a claim of exactly 5,000. Okay, where a failure is defined as a claim of larger than 5,000. Now there's no other outcomes there, so we have it's equal to 5,000 or it's greater than 5,000. There's only two outcomes there. It's binomial. There's two situations there. Let's double check that. So we have 5,000, that's one category, and 10,000 and 20,000, that's the other category. Now over here we have the probabilities. Okay, so it's 0.4 and 0.6 respectively. 0.4 of being 5,000 and 0.6 of being not 5,000, or in other words, larger than 5,000. Okay? Now, so let x be the number of successes in n trials. Okay, that's what we're told. And the probability of a success here is 0.4, which I've just described. Okay? So the question is to calculate the probability of 5. That's where we're getting n from, n equal to 5. 3 are for 5,000, that's 3 successes, and the other 2 are failures. Now, so if we're looking from the point of view of a binomial, we don't really need that, okay? Or it's redundant at this stage. Now, this is the sort of the theory notes regarding the binomial distribution. So there's sort of two things here to remember. Now, sorry, just actually one thing actually to just regard here is that this typesetting thing does not like factorials, so I just put in the factorials there. So the probability of x equal to k, where k is some value. Here what we're interested in is probability of x equal to 3, is n choose k times p to the power of k times 1 minus p to the n minus k. Okay, so here k is equal to 3. Sorry, k is equal to 3. And actually I should write that as a probability of x equal to 3. N is equal to 5. P is equal to 0.4. 1 minus p is equal to 0.6. And n minus k is 2. Okay, so it's essentially piecing it all together there. Now, I'll look at this part here, binomial coefficients. Okay, so I'll do that one out there. You have to practice with these, okay? So n is 5, okay, and k is equal to 3. So what we have here is 5 factorial over 3 factorial times 2 factorial, okay? Now 5 factorial can be written as 5 times 4 times 3 factorial, okay? And again 3 factorial times 2 factorial. So essentially up in the numerator you try and sort of simplify it down a bit or expand it out a bit, okay, like that, so that you can get a cancellation. Okay, so what we have here is, let's go back to blue, 5 by 4 divided by 2 times 1, that's equal to 20 over 2, which is equal to 10. Okay, so here we are. This is the final stretch. Probability of x equal to 3 equals 5 choose 3, which is 10. 0.4 to the power of 3, that's 0.064, and 0.6, which is 1 minus p to the power of n minus k, the number of failures, 2, that's 5 minus 3, n minus k equals 5 minus 3, and that's equal to 2, number of failures, and that's 0.36. So that's a little bit of calculator work, and you should get 0.2304. So probability just slightly less than a quarter. Okay, less than 25%. So ultimately, bit of practice, the key outcomes here, the key learning outcomes are just actually being familiar with these formulae, okay, formulas, both for the binomial and for binomial coefficients. But really the thing here was actually just spotting that we could use the binomial distribution for this, even though the question went at great lengths to hide that. All right, I think we'll leave it there.